Thank you very much, and thank you to Tori, who's been babysitting me the last 48 hours, and really been showing me an excellent time. I'm going to start my talk perhaps a little bit more philosophically than is usual for an SFI seminar. I'm not sure, but we'll see. That's partly because I'm kind of intrigued by some of the ideas I'm going to talk about, and I'm excited by their broader context and sort of how they fit in maybe with a bit of a history there. You shouldn't take the fact that I'm going to start very philosophically as an attempt to be grandiose. I'm not being grandiose at all. In fact, I'm going to talk about some things that are maybe kind of cute curiosities today, because I find them kind of interesting. And so that's the tone at which you should consider this. So the idea of helpful mechanical assistance goes back a long way in our culture, back to Homer and the Iliad. And these are examples of mechanical contrivances that do things in the world. They're constructed in order to achieve ends and to realize tasks. But if the idea of things that do things in the world has a long cultural history, when we shift to the intellectual tradition, we see a difference. We start to think of ourselves as humans, man the wise. And if you can trace through a long sequence of sort of influential and long-standing ideas that basically come up with this thesis that intelligence is about thinking, and thinking is all in the head. Right? This idea that we care about things like pure reason. Okay, and this is a long tradition, and this tradition has this dichotomy between mind and body, and they spent a vexing amount of time trying to discuss how to reconcile this dichotomy between these two perspectives. And mainly that's generated discussion, but I don't know that it's generated much more than that. There's also a long tradition that has considered how to formalize this notion of intelligence. Spent a lot of time thinking about, for example, how we define rationality or thought processes, not least of which is the logic tradition that started with Aristotle, but has now had many subsequent years of follow-up, including many kind of computational results recently. Now, as roboticists, our history of robotics shows that we're not immune to thinking of the separation between mind and body in quite stark terms. But on the other hand, our like day-to-day business is dealing with bodies of a mechanical sort. And so we're less likely to abstract the body away and say that's not that important. Right? So I would say roboticists are not likely to buy this kind of perspective wholesale. After all, we know that the terms on which an agent interfaces with the world is strongly influenced by the body that it has. So if the sort of classical point of view is not quite satisfactory, what else is there? Well, one thing we notice is that robots inhabit uncertain and dynamic environments, and this idea of having to deal with the environment on the terms that the environment presents to you is something which has been formalized and kind of captured philosophically, as well as important contributions from the American pragmatists who had this sort of realization that part of intelligent agency is dealing with the buzzing, glooming confusion of stimuli that the world throws up. There's also a contemporary philosophical school of the inactivists. They're all white men, but they're all live white men. They're not dead white men, but they're white men nevertheless. But they have this this point of view where they've attended very carefully to action, and also have they thought a lot about scrutinizing perception, and crucially scrutinizing acts of perception, thinking about that idea. Okay, and these philosophers will cite robot papers in their philosophical discourse. So when I teach this and I talk about this point of view to my students, we talk about, Dan Kodachek's collaboration with Bob Full and Rex. We'll talk about Rolf Pfeiffer or Rodney Brooks. These are people that inspire these folks. But the thing that we don't have at this point of view is such a long and rich tradition, such a well-developed tradition of theory, to think about the world from this kind of perspective. And so today I'm going to talk about some work we've done, which is contributing to the broader project of trying to formalize aspects from the sort of situated or inactivist point of view. Now, if these are words or names of people that you've never encountered, then probably the second word on the title of my slides, but not something you've encountered. So let me just give a definition of situatedness. And I first learned of this term from a book, Sciences of the Artificial, that Herb Simon wrote. And in preparation for this talk, I went back and reread parts of this book, and I was struck by how eloquent it was. In fact, I realized I can't do him justice without just reading from the passage directly. So I've got the passage right here, and I'll hopefully this will inspire you. It's a very worthwhile book to read. So maybe this will inspire you to read a book that you've never heard of it. So he tells the story of an ant on a beach. We watch an ant make her laborious way across a wind and wave molded beach. She moves ahead, angles to the right to ease her climb up a steep dunelet, detours around a pebble, stops for a moment to exchange information with a compatriot. Thus she makes her weaving, halting way back to her home. So as not to anthropomorphize her purposes, I sketch the path on a piece of paper. It's a sequence of irregular, angular segments, not quite a random walk, for it has an underlying sense of direction of aiming toward a goal. I show the unlabeled sketch to a friend. Whose path is it? An expert skier, perhaps slaloming down a steep and somewhat rocky slope, or a sloop beating upwind in a channel dotted with islands or shoals? Perhaps it's the path in a more abstract space, the course of a search of a student seeking the proof of the theorem in geometry. Whoever made the path, and in whatever space, why is it not straight? Why does it aim directly from its start to its goal? In the case of the ant, and for that matter the others, we know the answer. She has a general sense of where home lies, but she cannot foresee all the obstacles between. She must adapt her course repeatedly to the difficulties she encounters, and often lead to uncrossable barriers. Her horizons are very close, so that she deals with each obstacle as she comes to it. She probes for ways around or over it, without having much thought about future obstacles. It's easy to trap her in deep detours. Viewed as a geometric figure, the ant's path is irregular, complex, hard to describe. But its complexity is really a complexity at the surface of the beach, not a complexity in the ant. So that captures the idea, that's the antithesis of the idea that intelligence is all in the head, right? And that's kind of what this idea, this interplay between the ant and the beach and the role that both of us are playing is this idea of situatedness. So today I'd like to try to kind of talk about the situated point of view from a perspective of robots, and then try to formalize this and tell you why this point of view is kind of interesting and leads to a new form of motivation. So suppose I want to buy a very simple robot. This is maybe one of the simpler ones I can get on the market. So I go to iRobot and I buy a vacuum cleaning robot, and it comes with a base station with a docking target. And it's shaped in this particular way because it has a brush on the one side and it also has a wall following device on one side. Okay, so now imagine I happen to live, I'm not a government official, but I happen to live in a pentagonal world, and my robot starts at the top there, and I'm interested in the robot reaching the charging station. And it's a very simple robot. It has two controls. So follow the edge on the left of the environment, a little sharp turn, and then if the dock is visible, approach the charging station and dock. And has two observations, just if there's no charger in front or a charger directly in front, right? So in the creator has this, in the iRobot device, there's a little IR detector to tell you that. So then what I do is I model this environment and the modes with which the robot can interact with the environment in a graph form. So I'm going to consider about sequential decision making. And this is a particular graph where I represent action choices as square vertices and observation choices as circular vertices. Okay. So in this case, I've encoded a model here which maps directly into the environment in this form. And then I might say, okay, give me an idea of a plan for a robot that's going to solve this task. And the reason I wrote this description of the environment in a slightly unusual way to separate the actions and observations is because I actually want to represent a plan in precisely the same formal structure. I want to try to emphasize the duality between the 2 points of view. So this is what the robot's plan looks like. It looks somewhat like the environment. And so the robot starts in this particular location and looks at its plan. And the first thing it needs to do is choose an action. So it chooses action U1. And then it gets observation Y1 because the world says, okay, there's no charging station in front. So it gets a Y1 and it transitions to the next action. Vertex, and it does this again and again. It goes around until it gets to the point where now there's an observation telling the robot that there's a charger, and now it executes according to the plan, control U2, and the robot charges and it's all right. Okay, so that's an example of a description of a world specifically, and a description of a plan where I can think about the way these two pieces fit together in terms of a sequence of actions and observations that are alternating. And there's causation here in the sense that the robot picks the controls and the world picks the observations. Okay, so the claim that I want to make in the first part of the talk is that a situated view of the agent matters in a significant way. And I want to argue that the role that the environment plays is important. And specifically, environments can contain or impose regularity, and agents can exploit that. And that's going to give us the notion of the significance. So that's the thing that I want to show you. So let's get back to this example. And I want to consider a different plan. So here's a strange looking plan you might not have considered. But it has precisely the same semantics as before, which is the robot starts at the top there, and it's in an action vertex, so it picks an action, so it does control U1, then it gets an observation Y1 from the world, and then it gets to there, and it proceeds around like this. Now what happens is that we're in a situation where what's going to happen is that the robot is going to execute in the previous case. The robot is going to get to a point where it needs to choose an action, and the environment is not going to produce an observation at the time, which interleaves with the location where we make a distinction. So in the plan, there's two observation places where we care about whether there's three observation places, and there's only one case where we care about the distinction between a charger and a non-charger. In the other case, we do action Y1 regardless. So if you keep tracing this round, this alternative plan that I've shown you, it goes around multiple times. It gets to here, and now it gets observation Y2. And again, it doesn't care about Y2 versus Y1. So it charges around the third time. Okay, finally it gets to here. And now what's happened is that at this point, it takes the action and it gets to a point where it gets a Y2, and now it ends up taking the right branch and ends up in. Okay, so this is a weird plan, right? This is probably not the plan you would have thought of, but that's kind of the point. First of all, we have, unfortunately, a tendency to believe in the existence of the external world, and then we tend to imbue that idea directly in our robot. So if we think a robot needs to have a model of the world, we tend to think that that model of the world should look like how we think the world looks. But in fact, it's not necessary for us to take that notion of state so seriously. So here's an example where what's happening is the executions take lengths of order 15, because they're talking about the cycle length of 5 and the cycle length of 3. But their interplay still solves the task. Now, I'll admit this is you have a question here.
We have a question online. What is the difference between context and situatedness?
So, I mean, I would say I don't know a precise definition of context, but okay. And so in this case, in situatedness, in the way I'm kind of formalizing it, is that there's the direct kind of interplay of actions and observations here that give us, in this case, an execution that is more complicated than the executions which are in this environment or executions that are in this plan. Right, so the interplay means that I can't just look at the plan and tell you how the world's going to, how this is going to work out. I can't just look at the world and look and say this is how plans work. So this is an example, as I said, of a straight. Yeah, go ahead.
Why is it order 3, not order 2 on the right side?
So I will actually give you an example of one which is shorter as well. This has just happened to be a different plan.
Got
it. And indeed, that's not the shortest plan either. So we'll discuss another plan in a second. Yeah, this is intended to surprise you, to say, oh yeah, that's true. Actually, plans don't have to look like models of the world. Like, actually, plans are not about taking copies of state spaces and labeling them with actions. Like, you don't have to do that. What can happen is there can be an interaction between the plan and the world. As long as the interaction semantics end up arriving at the goal, you've achieved the task. So, and that's what this particular strange plan does. And it sort of reminds me of this film, if you've ever seen the Bill Murray film. It's about a spy. And the thing is, he's the sort of character who like bends down to tie his shoelaces, and then the bullet that's aiming for him shoots over the top of his head and it kills his enemy. And everything works out perfectly well in this world because he's kind of naive and he doesn't quite understand what's going on. But somehow there's this sort of interleaving where the semantics, the world is sort of sufficiently benign. Okay. So, so this robot doesn't know about the full state structure of the world. It might be thinking that the world is triangular, but in fact the world is not. But it turns out that eventually it gets an observation that tells it what it needs to see. Now, we were studying this just because we had this doubt. Mostly when we try to think about the existence of proofs of the existence of a plan, we think about plans that look like copies of the state space. And we were just asking, like, are there other plans that are out there? If you say there's no plan that exists, you've quantified over the set of all plans. Do we have a good description of the set of plans? And we encounter these unexpected plans. So we call these non-homomorphic plans because there's not a relationship of homomorphism between the plan and the world. And they do indeed exist. And it turned out that actually we've been doing work before that have been looking at these sorts of plans because we were interested in plans that look like this. We were specifically interested in the smallest plans that could solve a particular problem. So the usual metric we try to minimize is the execution cost. But if I try to communicate a plan to you rather than care about the execution cost, then I might care about the minimum plan. And this is actually maybe the plan that you perhaps first had in your head, when you said, oh, what I'm going to do is keep following the wall on the left-hand side until I see the thing and then I'm going to charge it. Right. That's not what an MDP would do, for example. Right? Okay, good. So in this talk, I'm going to focus on the idea of trying to do plan compression like this, because what I want to know is I want to ask, what's the minimum amount of information I need to achieve the task? And the insight is, and it's an insight that sort of shows up in a whole bunch of different places, if I can squeeze it down small enough, then what remains is the state which is necessary. That's the information that's needed. Everything else is extraneous. So you can see this in the form of a rank constraint in a linear system, or if you want to have an architecture which is going to squeeze your data through some latent space, it's the same idea, right? And in this case, the thing that I'm going to try to compress is memory. So I'm going to look at the number of these vertices. And now you might ask, okay, do we care? Do we count twice or what? I'm actually going to simplify that. So I'll show you in a second. We won't worry too much about that. But the reason that I made the vertices, the circles and the squares, was to kind of emphasize the symmetry between the robot and the environment. They're each playing an important role here. If you go look at your Russell and Norvig book on chapter 1, there's going to be a picture of an agent, which is a big block for an agent and a tiny thin sliver for an environment, because that's where they think the complexity is all in the agent, which doesn't have to be, right? Okay, so I know some portion of the audience are not computer scientists, so I'm just going to do a quick sort of reminder of automata. So this is an example of what we call a deterministic automaton. It's a state machine. It's labeled with a set of symbols. The symbols make up the alphabet. The alphabet in this case is ABC. Some of the states are designated special, like this one here with a double circle. Those are called accepting or final states. This object is it's a finite object, but it describes a sequence of strings, sequence of finite strings. So, and the way we find out that description, we call it the language, is we trace strings through this. So we're interested in strings that are start at the start state and end at the accepting state. So an example of a string that this accepts would be A, B, B. It also accepts strings C, 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 A, B, B, for example. There's also some strings like C, A, C, which you have trouble if you try to trace that, because you find there's no way to trace that. C, A, C, the second C doesn't have anywhere to go. That's called a crashing string. The semantics of this object say that that's not an accepting string. Okay. So I'm interested in memory minimization, and I'm going to consider systems that look like this and what we know about compression of those objects, and then I'm going to contrast them to the situated case that we're discussing. So this is very well-known kind of theory, which is this: is if you give me a deterministic automaton, you might ask the question, squeeze this down and give me the smallest one, which is equivalent. We have to have a well-defined notion of equivalence. The notion of equivalence is that I want you to find me something else, automata out, that has the same language. So that's why this whole language description is important. And the classic result goes back to Myhill and Nerode that tell us that we solve this problem nicely. Now let's relate this to robots. So I'm going to consider again our Roomba robot. And it's trying to get to a goal here. And I'm going to give it, it's got actions, which are just in this case, the bump actions. Sorry, the observations, just the bumper on the front. And I'm going to have actions that I'm going to label a sequential structure like this. And this is just sort of a compressed or a shorter encoding of the previous interaction. Okay. So I'm going to start, and it's going to say, while you're not perceiving a bump, you should do the green thing, which is to go forward. Then you're going to bump, you're going to take a right, etc. Right? So if you do that, this is going to cause this sort of execution. So if I look at this object, I say, that looks like a classic automaton. So it has some of the same structure. Let's try to do some reduction of that. So for reasons that I won't go into right now, these are called filters. I didn't label them that. And the person who did label them that said he regretted labeling them that. We can discuss that a little bit more, but anyway, he has said he would have called them something different. He realized that was going to work out, but anyway. So we're going to take a deterministic filter, and we're going to ask for the smallest equivalent deterministic filter. The previous notion of equivalence was language. I have to give you a definition of equivalence that makes sense here. Okay, so that plan is going to, I want to be able to come up with another plan as an alternative, and I need to be able to use that as a drop-in replacement for the previous plan. In order to do that, I have to give you a notion. I'm going to call that notion output simulation. So this is the sort of informal definition. Filter G output simulates F if for every input string that F can take, G takes that same input string and produces an output matching Fs. So the intuition is, if you give me an F, and you've got another G, and G can take the same inputs that F can take and produce the outputs that match, then G is a drop-in replacement for F. So if you think about each of these dots as a sequence of inputs and each of the colors as an output like we had in the previous picture, then if you give me an F that looks like this, then G must look like this. It has to agree on the inputs, and it's also allowed to do some other stuff on inputs it's not going to receive. So that gives us a notion of output simulation. And here's the surprising fact, which is that while the automata minimization problem is easy to do and it's efficient, it's in class P, minimization of the under output simulation of automata is an NP complete problem. The decision problem is NP. Okay. So let me just say a little bit about the complexity classes. So in case you've not kind of encountered those, or you've encountered them but you're not comfortable with them. So the complexity theory tries to tell us about relationships between problem classes. It adopts a specific computational process like maybe a Turing machine or something underneath. And it's often about justifying bad news. So the typical way that we use this is that you imagine that your boss tells you to find a solution to a problem and you don't find a solution. You come up and say, I guess I'm not smart enough. That's maybe what the situation you find yourself in. What you wish you could do is show up to your boss and say, you asked me to do an impossible task. There's no efficient algorithm, but we don't have that. So computational complexity gives us this middle ground where you say, I can't solve this problem, but neither can any of these other smart people. And actually, they're not solving the same problem. They're looking at closely related problems because we're doing reductions from one problem to the next. Okay. So the most classic thing to say, or the most famous thing to say, is this relationship between P and NP. And we suspect that P is not in NP, but they could be equal, but we don't suspect that. In this class, I'm just going to talk about things that are widely held. So we don't expect that E equals NP. And I said in the beginning, you need to pick a computational process, maybe a Turing machine. You don't have to care about the Turing machine. You don't even have to care about computational complexity. What you have to believe is if I tell you something is in P and I tell you something else is in NP, there's a robust and stark difference between those two. Because if you could show that there was not a stark difference between those two, you could get $1 million in your pocket tomorrow. Right? So lots of people have thought about saying that those two things are the same, and there's really a serious separation between them. Okay, so let me try to explain an intuition for this result that I said we proved as to what's actually going on here. So why is it that the filter reduction problem is harder? And it has to do with the nature of strings which come from the world. So let's look at this example. So in a classic automaton, I have, so sigma star are all the strings that I can take. And the filter that I can trace, it describes the pink strings there. Some of them are going to crash. Some of them are going to arrive in other states, but only some of them arrive at the pink. Okay. If I ask you to minimize things, what are you allowed to wiggle? You're allowed to take the white stuff and you can make it larger as long as it goes into stuff that was previously crashing, because that was not accepted. Or you're allowed to take things that were previously could be traced but could crash. That's the thing. But you've got to preserve this little pi segment. That's what you have to do in the language description. Filters are different. What you've got is you've got a sequence of strings. You've got a set of strings that crash, and inside those other ones, you've got outputs that correspond to each of them. So different colors in this case, right? And what you're allowed to do is you are allowed to grow the set of strings, but only to ones that previously crashed. Right? You have to preserve, you don't have to preserve the sizes of the colored segments, but you can't change the color of any of those segments. So what's going on here is that when we take that input, we're taking a description of strings that can arise. In the case of the robot executing a plan, the world has some observation sequences that can arise and some observation sequences that cannot arise. So that gives you that inner description. And you're welcome to come here and pick different choices for parts which are outside of that. But the problem is that that's, for a minimization problem, a combinatorial choice. So coming to this one and saying, I think I'm going to make that one blue. Maybe I'm going to make that one yellow. Maybe I'm going to make that one pink. Or maybe I'm going to make that one yellow, and then come back and say, I changed my mind. I don't want to make this one blue. It means you've got to go back and revisit all the previous. Go back and revisit all the previous things, at least as far as the best known algorithms exist. So the point is that because the world actually constrains the things that can arise, you change the terms on which you have to do this minimization. And that's where I'm arguing that the interleaving with the world, that constraints and that structure changes the complexity class. So the first part of the talk was to argue that situatedness matters in a significant way, and I took significant here to be a definition of a different complexity class for the minimization. Okay, so let's proceed a little bit further. So I want to start talking about actually you give me such a filter minimization problem, how do I actually do a minimization? Because even though the problem is hard, that doesn't mean we're let off free. We still need to, okay. And the reason for that is, well, as I'm going to get to, you'll see as we start to look at the sources of the hardness, we can get some sense of what's going on, other things which are arising. So in order to do that, I want to tell you about an algorithm for filter minimization. So this filter is like a DAG. It's not a real plan, but it's an example of a simple plan where in the beginning, the first action you do is the white action, and then you wait for an observation. If the observation is an A, then you perform the red action, and then the observation after is an A, you perform the pink action. And then the last thing you could get is this, for example. So what I would like to do is I'd like to minimize this, find me the smallest equivalent filter. Okay. And the key idea here is that what I'd like to do is I'd like to think about this by merging some states. So if I want to use fewer vertices, then I'm going to try to collapse them together. Now, the first thing is that if I collapse, say, a white vertex with a purple vertex, that's not going to work because I don't know what color to give you at that particular vertex. So the only real candidates to look at here are candidates that have the same color. And in addition to that, so if I make a compatibility graph, so these are candidates to merge, all I'm going to do is I'm going to draw some edges between things that are the same color. Now you will notice that there's no edge between W5 and W7, the two pink ones. They have the same color, but I can't merge them. And the reason I can't merge them is, well, suppose I had merged them together. And then after that, I arrived at that state and I received a C. The input specification here tells me that after that 5, I need to get an orange, and this one says after a 7, I need to get a blue. So if I merge 5 and 7 together, I won't be able to pick a color for the subsequent vertex. So we're only going to say that two states are compatible if they're compatible with each other if their outputs agree on their common extensions. Right? So they have a common extension C and they don't agree on that, so they're not. So once I've got a compatibility graph, there's a classic problem which is called the minimum click cover problem. So in Cook's original paper of defining the NP-complete case, NP-complete class, he included 21 problems. Graph coloring is a famous one, and the dual problem to graph coloring is the minimum click cover, which is in that same set of 21. So the minimum click cover is to find some number of sets of some subsets of these that cover every vertex, and every single one of the covering sets should have edges connecting everything inside that set. So that's clear. Okay. So this is the minimum click cover, and you might say, ah, great, I'm going to construct the minimum click cover. And then the natural thing to do here is, well, W0 goes to W0, and then, oh, the two purple ones are going to get merged, and then the two red ones are going to get merged, and then I'm going to get one from here, and I'm going to get one for there, and so on. Okay, so that's how you formulate this problem as a minimum click cover. Turns out there's a problem though here, right? So if you look at this vertex over here, you see that, well, we get two A's, and A's have to go in two different places. So we failed this determinism requirement that we should know how to trace that. So filter minimization is not the same as this NP problem of minimum click cover, but it's almost that. So it's almost that because what we can see here is we can see that we can see what the issue is here. If we decide to merge the two red ones together, then they're going to have A's that are leaving somewhere. Which means that if I'm going to merge these upstream ones, I better be ready to merge those downstream ones. Otherwise, there's going to be a fork. So I impose that as a constraint. Impose that as a constraint that I call a zipper constraint. So it says if you decide to zip these two together, then you better zip those two together. Or if you decide to zip those two together, you better zip those two together. Okay. So with these extra zipper constraints, I can enforce determinism. And now what happens is I get a filter that looks like this. Okay. There's something important in this picture here, which is that I've actually used the click cover in this to cover W6 twice. And that works out and the algorithm's all correct. But if you were a formal methods person who knows the history of bisimulation results, then you might say, oh, I know how to do minimization of these things. That's a bisimulation equivalence, and you have to take quotienting under the bisimulation relation. This is an example that shows this is false. This is not an example of a bisimulation relation. It looks very similar to one, but it's not. Because a bisimulation relation gives you an equivalence class, and that is not an equivalence class. That W5 has to go, 6 has to go into 2 places at once. It's not an equivalence class. So if everything I said in the last 3 sentences didn't make sense, that doesn't matter. But if it did, great, that was for you. Okay. So one thing I'll say is that actually, if you look at this directly, you ask how many zipper constraints there are, there can be bad news. There are actually exponentially many zipper constraints. So you can't quite solve this in exactly the way I said. You have to represent the zipper constraints implicitly and use a stat solver to do that. But it can be done, absolutely. And then there's another point here that maybe I'll come to in a second. So something else that is being considered is that if you have an NP hard problem or NP complete problem, you start to look at special cases and you start to ask, okay, what are the cases that are easy to solve? And it turns out that things like the filters were quite tricky because we looked at specific ones like, for example, trees. Then it turns out that trees themselves are actually no more efficient to minimize, for example. But there have been a sort of series of papers that collected special cases that were identified to actually be efficiently solvable. And they have examples like there's only one observation, for example. That's the unitary case. Or there's an observation that appears in exactly one place, only one place, for example. So we actually have a pretty good understanding of these different subclasses. But part of that understanding comes back to understanding this compatibility graph. Because it turns out that these subclasses, we've sort of found out a little bit later, correspond to properties of this compatibility graph. And there's certain compatibility graphs that have nice properties, like the so-called family of perfect graphs, which have a reduction order and so on. So things that are known about compatibility graphs here turn out to kind of map onto these specific cases, these efficient cases. I want to tell you about the next step that you can go beyond that. So the thing I said to you before, which is that you have a problem, your boss gives it to you, you can't figure out a solution. So what you do is you try to show that it's an NP hard problem. Then you say, well, don't blame me, you can blame everyone. We don't have a solution for that. Then your boss says, okay, find out if we have a special case. You can go and study the special cases. You can also look for an approximation algorithm. Another thing you can do is you can do fixed parameter tractability analysis. So that's the thing that we're going to describe in a second. And this is kind of a much more modern technique. So you may or may not have encountered this in one of your algorithms classes. So I'm going to assume you haven't and just give a little bit of a tutorial. So one of the classic NP complete problems is a decision problem called SAT or 3-SAT, where you've got a logical formula like this, where the A's and B's and C's are Boolean variables, and you have to assign them true or false values. And because this is an NP hard problem, sort of the best solution we have is essentially to enumerate all the assignments and to try all of them. So if you look at this case, okay, so how many assignments are there? There are 3 variables, so there are 8 assignments, right? So 2 to the power of 3. So you'll notice that although there are 4 clauses here, the brute forceness actually scales with K. It doesn't scale with M. So if I were to say, actually, I'd like to go and add an extra term on the end of that, you'd say, well, I'm no more unhappy than I was before, because that part I can do in polynomial time. So fixed parameter tractability is about identifying specific parameters of the problem. So in this case, the specific parameters are that there are 3 variables. That's what's important to understanding the brute force part of this. The other part is polynomial. So here's the case where I've done something longer, and I'm no sadder than I was before. Okay. So an NP hard problem is fixed parameter tractable. If there's some algorithm to solve it in time fkn to the on, where f is some computable function. So this is allowed to be kind of anything, and k is a parameter. So it's basically this picture here. It's a function which is costly, usually exponential, and then something else which is cheaper. And what we want to try to do is we want to try to understand what those parameters are, because they give us a sense of where the hardness lies. So I can tell you a little bit about this in the case of filter reduction. So in filter reduction, we have a result that was a wafer in October, which shows has this kind of horrible form over here, but it has a bunch of different parameters that we kind of learned about. And what's important about these parameters is that they are essentially modifications of the parameters that exist for the original click cover problem, but they are enriched by looking at the structure of the compatibility graph, the zipper constraints. So you look at the zipper constraints, and you can look for the width and the height of those compatibility constraints. So the more constrained those are, that's what's going to give you something which is harder. Okay, so we have some sense of how the zipper constraints are making this problem harder. So that part which was missing. Okay, so now I want to go back to it. I want to talk about a slightly different variation of this problem. Which is, I want to consider the case where I have something that looks like a filter from before. But now what I'm going to do is I'm going to allow us to go and label some of the vertices with more than one color. So what's the meaning of this? So in the previous case, we were looking at a description and we had actions that were labeled each time. So it was like forward or left. So if you imagine you've got a solution to a problem where there's more than one way you can solve a problem, more than one action will make progress towards a goal, you could encode that by just kind of labeling this thing with more than one color. Okay. So let's see. So this is an example of what I've done is I've skipped some slides here, so I'm going to have to back up a little bit to kind of say what's going on here. So in this case, this is a particular example of a problem where you can minimize this in a particular way. So ignore this A, B, and C. Just ignore these two things for a second over here. Okay, and just look at that example filter above. So the object below there is an example of a filter which actually satisfies a slightly more general version of output simulation that I was discussing. So this object is now no longer a deterministic automaton, no longer a deterministic object. So the previous case, I gave an example of an automaton, and you trace that automaton through, and there was never a case where there were two A's. When we encountered two A's, we were like, well, what do we do in this? Okay, so it turns out that that family of objects, those non-deterministic automata, are extremely well studied themselves. And they express exactly the same family of languages that the deterministic ones do. But they are a great deal of interest because it turns out that those can be much smaller, right? So actually exponentially smaller to express the same language. Their existences are exponentially smaller. So then we ask the same question. If you can use non-determinism to compress a deterministic automaton exponentially, could you do the same thing with a filter? And it turns out that the examples that work for automata do not work for filters. But there are examples of filters where non-determinism does allow you to do some compression. So if I take this thing and I remove the C's for a second, and I ask you to compress that filter at the top, actually the smallest filter you get is the filter at the top. I think that's right. No. Sorry, it's a bit. I'll show you the numbers in a slide in a second. You take this one and you then compress it down to a non-deterministic case. What you find is that you can do this thing where you can squeeze down by using the ambiguity of the non-determinism. So here you'll see, for example, the top, if I get a string, well, I've got a string here, AC. If I trace AC, there's a tracing top there that goes AC and it gets me to teal or purple. If I do the same tracing in the bottom, AC, I can end up in two places. I can end up here, AC teal or AC purple. Both of those correspond to an output which is consistent with that. Okay, so it turns out you can do compression to a non-deterministic case, but there's something which is unusual. So in the automata case, we have two interpretations of what it means to trace for a string to be in the language for a non-deterministic automata. First case is, if you give me a string and I ask, is this the language? I ask, is there any way you can trace it such you can reach an accepting state? You have to find find some tracing. That's one interpretation. The other interpretation is sometimes you trace it and it crashes, and then what you do is you rewind and you revisit some of the previous choices you made before, and then you trace it forward. These are two statements about how we think about non-determinism, and they're actually equivalent in the automata case. But they're not, those two notions of non-determinism do not apply directly to filters for the following reason. Consider the string AC. Now imagine I trace the string ACC. So I've added this orange, and I've added this blue, and I've added this orange, I've added this blue. I can trace AC in a way which is consistent below with the version which is above. All tracings below are consistent with the version above. But now if I come and I trace the C to here, or to here, and I say, oh, I need you to trace a C which follows on from there, because in this tracing ACC, I want this to come to orange. You say, okay, that's okay on the left-hand branch. This branch is going to crash. But I'm going to say, I can't do that if I'm using this as a plan. I'm using this as a plan, and I'm tracing forward observation A and then observation C, and then I produced purple. Then you can't go back and say, well, actually, I changed my mind. You need to produce teal and then orange, because that was an action you just did in the world, right? You can't undo that. So you might say, okay, well, that's fine. Just add a C from here to here so that you can rescue that. But the problem is, if you do that, then you'll see now that BCC in the top, which goes to blue here, cannot get to there. So let me recap. There's an example, so there's this idea of nondeterminism, which can allow additional compression. There is a way of defining nondeterminism that makes sense in the filter case. But it's problematic because you can't do this rewinding because the world is causal, not just something that you can undo, right? So the fact that you're interacting with this thing in the world it changes the nature of this ability to do nondeterminism. Okay, so there's a new definition that we kind of invented here to say a filter is string single outputting if for every string in its language there's precisely one output or one color associated with it. So here's the thing, that in this case, if I have ACC and this was purple, orange, and this was ACC and this was also orange, then I'd be okay because I could say, well, it turns out that, well, either in this case, AC, if this was teal, I wouldn't have to backtrack. I could jump to a different place in my plan, but the sequence of actions that I had produced in the past, in the real world, is consistent. So it allows strings for strings to be traced multiple ways, including for some of those ways to crash. But in those ways that do not crash, they must agree on the output they produce. And even when the filter's outputs may produce side effects, the backtracking and superposition interpretations of nondeterminism disagree. Right. So if this was teal, I could, in my mind, backtrack and then start executing from here, because what I actually committed to the real world would be consistent with that. So this seems to like rescue the idea of executing in the real world, but is this class of non-determinism actually meaningful? Well, I'm going to try to argue that it is. I'm going to try to show you that it is. So all deterministic filters are string single outputting filters because they trace in exactly one way, so they always produce one string. String single outputting filters are a subset of non-deterministic filters because they're non-deterministic filters with this extra proviso. So it's just if you relax a constraint, then there are ones that are in here. And the example that I showed on the previous slide was one which was in there and not in there. So this is a smaller class that lives between these two. And so this seems to be what I'm calling sort of a weak form of non-determinism. And so this is to kind of touch on the thing that I said before, which is we went from deterministic to deterministic. We were allowed to go from deterministic to non-deterministic automata. This is an exponential decrease in size. Here we have something where there's a reduction in size. And now string single outputting filters fit in the middle. And I'm going to try to convince you that actually this is a strict separation. So this idea of non-determinism I've introduced, which is a separate form of non-determinism from the classical theory in computing, actually is a well-defined class by itself. And I'm going to do that by just giving you an example. This is sort of the filter we had from before, the tree we had from before. It has 36 vertices. And if I minimize each of them, subject to each of those constraints, I get one which is 21, 22, 23. So there exist minimizers that are in this class that are smaller than the deterministic ones and are not as small as the non-deterministic. So this is a second case where acting in the world affects things because the world is not something you can rewind, right? And so the sort of consequences that we've invented in some sense a new type of non-determinism that doesn't exist in the classical theory because of the fact that we take the world seriously. And then one thing I should say is we compared P to NP, but this is also a well-known result, which is that this is a P-space complete problem, and that's a complexity class which is widely believed to contain all the NP complete problems, but to be larger. So in the same way that P is not believed to not be equal to NP, NP is not believed to be equal to P. And you can see that something interesting has happened here. In this case, we actually see a hardness separation for the deterministic to deterministic case. But down here, this problem is already so hard that we don't kind of get harder in this case. Okay, so let's see. I've got a few more minutes here, and I want to just talk about a few additional things that I haven't touched on so far. which is that I've been drawing these graphs. So this is an example of a graph I had from before. And I've been asking questions about whether I can make a transformation, and this transformation will preserve behavior in a way which is a drop-in replacement. This idea of output simulation. One of the things that I've done is I've sketched very, very, very simple examples of robots, right? Sort of like the simplest case I can construct to kind of make the point that I want to make. And so I labeled the world or the plan with edges that look like this, labeled with an observation. And I didn't say anything about that, but you may have noticed that I put braces around those things, because those are actually allowed to be sets. And in general, that doesn't make a huge amount of difference in the classical theory of how we treat these sets, because after all, they're finite. There's a finite alphabet, so you just list them. But if you think about the sorts of inputs that we get for our robots, they often look like something like this, an output from a LiDAR or something. It's a very large set. So it turns out the operations you can perform on these objects don't actually depend on this being a finite set. They depend on that being a set for which you can compute the containment of an element in that set. So if I have a description of half of the LiDAR readings here and half of the LiDAR readings there, as long as when I get to this observation, I can look at the LiDAR reading I have and decide which one to take, I'm actually fine. Okay, so, but the reason I want to touch on this is because there's a little bit of a hint towards the fact that we might start to think about other behavior preserving transformations. So the ones I'm going to discuss right now are sensor transformations. So this is the way I kind of think about it. Suppose I give you an idealized range sensor. So let's talk about it in a planar world. And suppose this gives me, for every angle, it gives me a reading between 0 and infinity. It's like the perfect LiDAR that you can buy, right? And I happen to give you a robot, and in my environment, I study that it can avoid this obstacle and it can get down the corridor where I want it to go. So I give you a check mark because I say, if you give me the ideal sensor, I can solve the task. Then what I might do is say, well, it turns out I don't have the ideal sensor. I have this old sick LMS. And I can describe that by taking this ideal range map, and I can take some of the values, like namely half of them, and I can squish them to 0. And I can take these other values and I can stop them, rather than going to infinity, I can stop them going to, I don't know, 8 meters out or whatever it is, 12 meters out. So this gives me a map which takes this input and reduces it, right? So I'm losing information because I've gone from the ideal thing and down to the real thing I can buy. And the question I might ask is, well, can I still execute this behavior? That's a question. That's why there's a question mark. Okay, but another thing we might do is say, well, actually, I've got a different LiDAR. This is a different set of specifications. I have a different map, H2, which tells me how to take the ideal thing and realize it this way. Or even if you want to go really old school, you could think about a sonar ring in some way. Or I was having a discussion earlier, you could have a bump sensor, which just maps all the ranges down to like 0 and epsilon, which tells you the bump, right? So for each of these cases, what we're asking, okay, if you have a certificate that you can achieve this with a plan. So specifically, if I give you a plan like one of the ones I gave you, and it has these labels from ideal observations, what happens if I take this map H and I apply the map to each of those observations? That's going to reduce those down to the things that I can actually disambiguate. And then I can ask, can I still preserve output simulation? So that's the question of, is application, we call this a label map, this destructive or not? And you can ask questions like, for example, you might be interested in what is so I have to give you a definition of coarseness of label maps, but you could think, okay, some label maps are more destructive than some are less, but I could ask, what's the coarsest label map that preserves the behavior? So, and it turns out that I can tell you that that's a hard problem to solve in the sense that I have a hardness result showing that you can't actually do that even in simple cases when you can't do that efficiently. That's an NP1 problem. But that is a problem one can go and study. You can look at taking label maps and testing them and seeing if they're effective. So that's an example of sensors that are modeled through sensor transformations, and you can see they have implications for robot design, specific, and I should say robot design, like from the question of the choice of sensors, right? Or maybe you're not happy with either of these sensors, but you know a company that will make you a custom LiDAR, and you might, through this, be able to give them specification of what you're looking for. All right, and one other transformation you can consider is if you've seen, this is an RGB camera, that's an example of an output from an event camera. You might ask, can I take a sensor and eventify it to understand what an eventified version of that is? And you can do the same thing. You can ask, what are the transformations? In this case, it's sort of like a derivative. It tells you something about the change in the signal space. And you can ask the same question. Can I can I transform a sensor to its event version and ask, is that destructive? Okay, so I'm 30 seconds over time, so it's time for me to wrap up here. So we're on my summary slide, so I've got a few quick things to say. So the talk started by looking at Simon's parable of the ant wandering on the beach and talking about how environment-agent interaction is important. And so I tried to model those two as symmetric, thinking about action and observations being picked sequentially. And then motivated this idea of trying to figure out what's the essential knowledge which is needed and getting to that by doing compression. And then showed that non-situated automata, that minimization problem is very different from the case where actually the world constrains the sorts of strings that you will interpret. And that separation gives you additional opportunities for compression, but the flip side is you've got to figure out how to make those combinatorial choices. And we looked at some special cases very briefly and discussed parameterized complexity to give some sense of those hard results. And then sort of briefly, I talked about generalizing to non-deterministic cases and the fact that we're being causally constrained also results in different sorts of behavior. And this gives us a different genuine class of non-determinism, which has not been studied before. And then there are many other things which are interesting to model under this idea of output simulation, including, for example, these sensor transformations, or there's the dual to that actuated transformation, which I didn't talk about. Okay, so this is a collection of different ideas which are drawn from several papers, but including this idea of concise planning and filtering, which is where I said we started in the beginning of understanding that we were making small plans and then started to study these things all the way down to the fixed parameter tractable result that I just touched on. So with that, I'll stop and take any additional questions.
I have a question about the motivation for like representing everything as a kind of very small automaton. So in the real world, I guess few things really can be represented as this because there's so much noise, there's so much complexity. And I can see how, you know, in maybe a man-made environment this can work. But how do you see this? Do you think that we will have like generally applicable robots in the real world, like outside, not in man-made environments like this?
So there's a slide that I removed that maybe I'm regretting removing. Because I think, let me paraphrase your question a little bit. You're saying like, okay, I saw these automata-like descriptions of plans. They seem so clean, and nothing I've ever encountered in a robot looks that clean. So the slide that I removed was an old paper where they were solving a POMDP and generating a policy. And the way that they're representing that policy is through a graph, which has a structure which says take in observations and produce sequences of actions. So I would argue that no one has ever built a robot that did anything other than take sequences of observations and produce actions as outputs. Point me to someone who's done something whose controller does anything other than that. Sure, it may be generating the graph in real time, blah, blah, blah. Okay. Of course, I'm studying like very, very crisp, tiny little examples. But there is a very valid observation here, which is that I'm talking about something like taking a plan and compressing the plan if I have the whole plan. If you say, well, look, in practice, I use model predictive control to produce my plan. The one thing you don't have is the plan in front of you that you can compress, right? You've got a procedure that generates the plan as you need it. And that's a perfectly reasonable thing to do because that plan is, who knows how big that plan is, right? I mean, there are cases where there's no reason to suspect that that plan is even a finite graph. So, you know, realistically, we've done some work where we tried to look at this question from before on the sensors in particular. We were looking at trying to like probe the decision boundary between sensors which are destructive and the sensors which were not. But we did that often in tasks which were quite simplified in the sense that we would think about an environment like a campus. We would build a Voronoi decomposition of the space, we'd build a plan on that, and we would explore that. But it's certainly, I haven't really answered the question of where plans come from, right? I just said I have a plan, and I also have mainly bad news about plans, right? In the sense I have bad news about compression of those things and so on. So my hope is that really what happens is what I hope is that I've made something which is a bit nebulous, like when I read Simon's Ant, I think like, yeah, I really get that. But I read that when I was a grad student years and years and years ago. I was never able to kind of put something more concrete to that. So my hope is that I've picked some really simple examples, like I've made that a really crisp idea, like, yeah, there is a difference between when the environment is contributing and when the environment isn't contributing. That's maybe a useful fact to know, but I don't, maybe it doesn't change the ROS 2 code you're writing right now, right? I recognize that. On the other hand, there are a lot of people writing ROS 2 code right now, so I'm trying to do something, say something a little different, I think. Yeah.
I'm just thinking about like this interaction between the environment and like, is it fair to say that the sort of uncompressed plan is like preparing for the worst case possible environment that doesn't have structure, and that like by sort of finding a way to say, well, the environment's actually not as adversarial as you thought it was?
Okay, yeah, so that's an excellent question, and I should have tried to make that a little bit clearer. I didn't quite in the time I had. So in this model, when we say you have a plan, we mean that you have a plan that you're guaranteed that you can execute that will get you to the goal, regardless of what observations the world picks. Now, the world's hands, if you like, Mother Nature's hands or whatever, are tied in the sense that she can only pick from that graph. So, in the model earlier on, it didn't get to say there was no charger when there was a charger there. If there had been a Y1 instead of a Y2 there, then we could have argued, well, that task is actually impossible to achieve because there's too much sensory aids.
I'm sort of thinking of adversarial in terms of when the world was designed or whatever. Like it could be like that if the Pentagon room was so much more complex, then there wouldn't be a simple plan, but maybe a simple plan exists because the environment is actually nicer than.
Yeah, so I don't know the answer to that. As a grad student, I started to think a lot about environment complexity, and I don't know how to separate that out from understanding what the robot does with the world. After all, the world can be incredibly complicated, but if you're like, a one bit of amoeba, how complicated is it, right? It's the sequences, the stream that you get. So I think it's kind of important to try to view the complexity of the world through the way the agent is going to perceive it. But there's something else which you said, which is, so what if I told you I know nothing about the world? So then I can say, well, you can get any observation at any point in time. Turns out that if I tell you that and I ask you to minimize that, that's actually an easy problem to solve. We might get a very big plan, but you get a certificate saying that that's the smallest one, very cheaply. So why is that? If you go back to my pictures with the Venn diagrams, those colors are pushed all the way out to the boundary. There's no room for you to make some combinatorial choice. So I don't know if that's good news or bad news, but that's what that is. And it turns out that like those other properties on some bisimulation relations have to do with those cases when actually you have to be ready for all observations. But yeah.
Is someone online trying to ask a question? Like, there might be, but I
Drop
don't.
the mic, and we're just hearing the mic that was dropped, I guess.
Then are you trying to ask something?
Maybe I can ask one last question.
Yeah, please.
So you briefly glossed over the identification paper.
Yeah.
Can you maybe briefly summarize like what is the main point of identification, or like what, because in this other label mapping it was about the impression of the sensor data, right? Whereas here it's what is
right.
What is the motivation?
So in this case, we take an observation and we make some transformation on that observation and we produce another observation. In the eventification paper, we're imagining something like so imagine some other sensor, sub-sensor where what you're interested in is you're interested in changes in sensor readings. So if you happen to get the same LiDAR reading 10 times in a row, you don't get 10 separate symbols. You have to somehow get blank symbols somehow. So in the sensor eventification case, what we're doing is we're doing a transformation where you're allowed to map the symbol from one output to another output, but you're also allowed to do some things like drop some of them. So what happens is that the action observation interleaving kind of goes away in some sense because you may be missing some observations. So the paper really formulates the appropriate way of thinking about. I think, I mean, I could be wrong, but I think we've got the right definition for the idea of trying to understand what happens when the streams are not length matched. And it shows that there's some cases where it turns out that something like a sensor which stutters, which gives you extra readings, and a sensor which drops some readings, those actually have almost the same power. So if the task can be performed under the task on the original sensor can be performed under one which hallucinates extra readings or ones which drops extra readings, those are basically the same case. And in hindsight, that's a little obvious because what you're doing is you're obviously not using the length of the sequence. You're only using the data which is in the sequence. What the paper is doing is it's actually defining, in some general sense, a notion of a derivative on a sequence. That's what it sets out to do. It turns out like the word event because they don't call. Sometimes they call these sensors event-based sensors. If you try to get a definition for what event-based, you'll find many different definitions. There's event-based programming, right? There's event-based sensors in this form. There's event-based models, for example, and they all mean something slightly different. And so the paper kind of gives, in some sense, like five formal definitions of what you mean by an event-based transformation. And then it provides algorithms that says, oh, you have a filter that solves this task. You have this transformation. And you want to answer whether it's destructive, make this transformation and check this result. And if it succeeds, it will give you an existence of a plan that will work under that. And if it doesn't succeed, it will tell you it doesn't succeed because there's aliasing in exactly this place. So it has those sorts of ideas. It's a bit more complicated because it's also kind of compositional in its nature. But thank you, excellent.
Question? I think Regina may be typing a question. Okay, I think we're going to, okay, so the question here is, does the speaker know about the work of Letterman-Klatsky exploratory procedures?
He does not, and he ought to. Hang on, can you tell me how to spell that?
It's Lederman and Klatsky, Klatzky.
Oh, thank you. No, but I need to. Oh, thank you. I don't even know who those authors are, so that's a good. Thank you, Regina. I will look that up.
Thank you for your response. We are going to have to end the seminar. You have another meeting to get to. Thank you guys so much for coming. Look out for next semester's schedule for SFI seminars.